Hi, I'm Mark Barsamian. In this video, I'll be doing examples that are applied problems involving the chain rule. This material is from section 3.4, the chain rule, but more specifically, there is no actual discussion or examples of applied problems involving the chain rule in section 3.4. But that's okay. We don't really need book examples or book discussion. We've got lots of examples involving applied problems in book sections 2.4, 2.5, 3.2, and 3.3. All those applied problems involve the same general concepts. The only thing that varies is the particular technique used to find the derivative. Now, the corresponding homework for this video is this collection of two problems from section 3.4. Now let's review a couple of things from earlier in the semester. First of all, from very early in the course, the idea of average rate of change. Remember that these words, the average rate of change of f from x equals a to x equals b, that means this quantity, this difference quotient. And the interpretation of that, the graphical interpretation, is it's the slope of the secant line that touches the graph of f of x at these 2 points. Also remember this diagram showing three equal quantities from the video for homework 33. At the time, I mentioned that this was going to be the most important concept for the second month of the course. I have neglected to actually review this diagram in videos since then, but we have been using this idea many times. The idea is this, that this expression, f prime parentheses a, that is the value of the derivative of f at x equals a, is related to two things. It's the number that's also the slope of the line that's tangent to the graph of f at x equals a, and it's also called the instantaneous rate of change of f at x equals a. Both those concepts, the average rate of change and instantaneous rate of change, are going to come up in the video today. Remember our derivative rules from chapter 2, the basic rules, from chapter 3, the exponential and logarithmic function rules, and from chapter 3 also the product rule, quotient rule, and now the chain rule. All right, we're going to do two examples today. The first example is this one involving a company that makes ventilators. The daily cost function is this function. In this function, x is the number of ventilators produced each day, and c parentheses x is the cost per day in thousands of dollars. So questions A and B have to do with these quantities. Well, c parentheses 0 denotes the value of this function at x equals 0, so we just simply substitute in x equals 0. So c parentheses 0 is 300. C parentheses 16 is the number 460. And C parentheses 91 is 860. Question C is to find these two quantities, C prime parentheses 16 and C prime parentheses 91. Well, to find those, we need to find C prime of x first. Now, in order to get C prime, we should rewrite the function C of x. C of x is this function, which is given in radical form. We should rewrite that in power function form. Okay, now we're ready to find C prime of x. So there we use the sum and constant multiple rule. That constant multiple of 40 slipped right through that derivative symbol. But the number 60 is not a constant multiple, it's a constant function. So its derivative is 0. So we recognize the form of a composition of functions, and so we use the chain rule. Now, as I've done on all earlier problems involving the chain rule, I do the chain rule details off to the side. So the inner function is 4x plus 36. So inner prime is just the number 4. The outer function is parentheses to the 1/2. That's a power function. That's the empty version. We find its derivative using the power rule. So its derivative is 1/2 times parentheses to the negative 1/2. But as is always the case, when we end up with an expression that's in power function form, we want to convert it back to a more convenient form, either positive exponent form or, in this case, radical form. So there's our outer prime. So we're ready to assemble all the parts to make C prime of x. So there's my outer prime, and I need to stuff it with the original inner function. And then I need to multiply by inner prime, which is just the number 4. And notice that I have written that number 4 up on the baseline, not down on the floor. Now I can simplify this. Notice that that 4 and that 2 cancel, turns that 4 into the number 2. So I end up with this. So that's my C prime parentheses x. Now we need C prime parentheses 16 and C prime parentheses 91. So I get that C prime parentheses 16 is the number 8. So C prime parentheses 91 is the number 4. All right, let's go on. Interpret the results of A, B, and C. Well, question A was this. Question B was this pair of values. And question C, these results. What do those things mean? Well, let's go back up and remember what our function means. C of x is the cost per day in thousands of dollars for making this many ventilators. So these three results in A, B, and C are the costs of producing certain numbers of ventilators. Well, look, in question A, no ventilators are produced. So the resulting value of C was 300. That tells us that if the company does not make any ventilators, they will spend $300,000 a day. Those represent what are called the fixed costs for the company. $300,000 per day for not producing any ventilators. It's just the cost for paying payroll, paying building rent, whatever other costs the company has that don't depend on how many ventilators they made each day. So the fixed costs are $300,000 per day. Now notice that that's units of thousands of dollars. Now what about these results? C parentheses 16 and C parentheses 91. Those are the costs of producing 16 ventilators per day or 91 ventilators per day. And the costs are in thousands of dollars. So if the company produces 16 ventilators per day, their costs are $460,000 per day. All right, so there are our interpretations of A and B. What about our interpretations of C? In C, we found the values of the derivative, C prime parentheses 16. Now remember that this means the rate of change of cost. Also, when we were discussing marginal analysis, we saw that this quantity is also called the marginal cost, and we saw that it could be interpreted as an estimate of roughly how much the cost will change if the quantity produced is increased by 1. So this number, 8, is an approximation of how much the costs will change if the production changes from 16 ventilators per day to 17 ventilators per day. So another way of saying that, some terminology that the book uses, is this would be roughly the cost of producing that 17th ventilator. So if the production changes from 16 ventilators per day to 17, that is, if the production number goes up by 1, the cost will increase by roughly $8,000. And so that's what the book would call an approximation for the cost of the next ventilator, or the 17th ventilator. On the other hand, if the production is 91 ventilators per day and production increases to 92 ventilators per day, then the approximate change in costs will be this number, C prime parentheses 91, which is 4. So if the production changes from 91 ventilators per day to 92, the cost will increase by roughly $4,000. And again, that's what the book might call the cost of the next ventilator. So looking at the big picture, when you're at a production level of 16 ventilators per day, the cost of the next ventilator is $8,000. If you're at a production level of 91 ventilators per day, then the cost of the next ventilator is only $4,000. So the trend is that the cost of the next ventilator goes down when your production level goes up. That's the interpretations. Again, it's explaining in words what those mathematical results mean. So in writing those interpretations, we use that important concept that I showed at the beginning of the video. We are asked to interpret these mathematical results, so our interpretations are about rate of change or about y values. Let's go on. Question E, illustrate each of those quantities on the graph of the function. Well, let's go back up and look at our quantities. In A, we found C parentheses 0, C parentheses 16, and C parentheses 91. There are these three numbers over here. Those are all y values on the graph. So we just illustrate those quantities by writing the coordinates on 3 points of the graph. So let's go down and label those 3 corresponding points on the graph. So there are 3 points with those numbers, 360, 460, and 860, that we got as results in questions A and B. And again, those are y values on the graph. In the cost function, we should label its formula. Now, how do we illustrate the result of the quantities from question C? In question C, we found these derivatives, and we found the values of the derivatives at those particular x values. Well, let's go back up and review that important diagram. We found these quantities in question C. We interpreted them, that is, we wrote what they told us about the costs. That was one of our jobs, was to interpret them. And so we used the language of rate of change. But now we're supposed to illustrate them on a graph. So for that, we'll use this idea, that the values of those derivatives correspond to slopes of tangent lines. So if we want to illustrate the derivatives, we draw tangent lines and label them with their slopes. So we put a tangent line on the graph here at this point and another tangent line here. And we label those tangent lines with their slopes, and notice the tangent line here is steeper than the tangent line here. So that's the idea that the cost of the next ventilator goes down as you go up in production. The slope of that graph becomes less positive. Okay, that's the end of example 1. Let's go on and do another example. Example 2, we have a drug that's administered by injection, and the drug concentration in the bloodstream T hours after the injection is given by this formula, and the value of the concentration is milligrams per liter. So question A says, find the concentration after 1 hour and after 4 hours. All right, well, we have a formula for the concentration, and we're supposed to find the concentration after 1 hour and after 4 hours. So that just means to find the value of this function at those times. So we get the answer that C parentheses 1 is 3 over square root of E. Now we'll type that into a calculator in just a minute, but let's go ahead and get C parentheses 4. All right, so C parentheses 4 is 3 over E squared. So now let's get approximations for these. So when you type these into a calculator, you get roughly 1.82 and 0.41. Now we are asked for concentration, so we have to give these answers with units. All right, let's go on. Question B. Find the rate of change of the concentration after 1 hour. Now, they only give one time for the rate of change, so that must be an instantaneous rate of change. So here we've used that important connection. We're being asked for instantaneous rate of change, and we're supposed to make the connection that that means to find the derivative at that time. So the strategy should be find C prime parentheses t and then substitute in t equals 1. Okay, so we have to get C prime parentheses t. So we have to take the derivative of our concentration function. That function is here. 3 times e to the minus t over 2. Okay, so in this step I've used the constant multiple rule. And also I've used this little trick. Instead of writing minus t over 2, I wrote minus 1/2 times t. The reason I did that is because I can find the derivative of this using exponential function rule number 2. Remember what exponential function rule number 2 looks like. Exponential function rule number 2 says the derivative of e to the kx is k e to the kx. So there, we used exponential function rule number 2 to replace this expression with this expression. The derivative of e to the kx is k e to the kx. And then we simplified. So there's our derivative result. It's this. So now we have to substitute in t equals 1. So that's an exact answer. So I should label on our previous computations the exact and approximate. So in this calculation, here were our exact answers, and then here are our approximations. And in this C parentheses 4, this was the exact answer. The only way to write 3 over e squared exactly is to write 3 over e squared. And then we had this approximation. So in the current problem, there's our exact answer, and we'll type that into a calculator, and the result is 0.91. Now it looks like I've forgotten a minus sign. There's a minus here, and so the approximate answer is minus 0.91. Now we need units. We're trying to find the rate of change of concentration. Now remember, the rate of change will have units that are whatever the units of the concentration are divided by whatever the units of the time are. The units of the concentration are milligrams per liter, and the units of time are hours. So the units of the rate of change will be milligrams per liter per hour. Now let's go on. Find the rate of change of concentration after 4 hours. Well, here again we're being asked to make that connection, that what we're really being asked for, or the way that we'll find this, is that we'll find the value of the derivative at time 4 hours. Now remember what this means. It means we're going to substitute in t equals 4. So let's substitute in t equals 4. So there's our exact answer, and we're supposed to get an approximate answer as well. If we type this into a calculator, we find the following. So the result is approximately minus 0.20. Now remember, we were asked for rate of change of concentration, so we've got to give the correct units. Okay, let's go on. Question D. Find the average rate of change of the concentration from 1 to 4 hours. Well, notice that this question gives 2 times, and the previous questions gave just a single time. Remember, in question B, we ended up finding an instantaneous rate of change by finding the value of the derivative at 1 time. Question C, we found an instantaneous rate of change at 4 hours by finding the value of the derivative at 1 time. In question D, we're being asked for an average rate of change, and 2 times are given. Well, remember the definition of average rate of change from the beginning of this video. The average rate of change of a function from one value of x to another is given by this calculation. So we need to do this with our concentration function. So there's our expression for average rate of change. Now we need to get our expressions for C parentheses 4 and C parentheses 1 and put them there. So this expression and this expression. Now dividing by 3 is the same as multiplying by 1/3. And then you can see that the 3's will cancel. And there's our exact answer, 1 over e squared minus 1 over square root of e. Let's type that into a calculator, and the result will be, the result is approximately minus 0.41. But we need to give units. So the units are going to be whatever the units of concentration are divided by whatever the units of time are. So notice that in B, C, and D, the rates of change were all negative. So in B, we found that the rate of change was this. That tells us that the concentration is decreasing at that rate. Concentration is decreasing at that rate at that time. So 0.91 is the rate at which it's decreasing. In other words, C prime parentheses 1 was a negative quantity, a negative number. in question C. This result tells us that at time 4 hours, concentration is decreasing at that rate. And finally, question D, this tells us that over that 3-hour period, concentration was decreasing on average at that rate. So the average rate of change was negative, so when we describe this in words, we'd say that the concentration was decreasing at a rate of 0.41. Let's go on. There's one more part to this problem. Question E was to illustrate those quantities from A, B, C, and D on this given graph. Well, remember in question A, the results were Y values. So we found this, C parentheses 1 is 1.82 roughly, C parentheses 4 is roughly 0.41. That gives us XY pairs or TC pairs on our graph. So we illustrate those quantities by labeling those points with their coordinates. So that's an approximate Y value, 1.82. And there's an approximate Y value there. All right, so we've labeled those points with their coordinates. We've labeled the axes on this graph. Now, how do we illustrate the quantities in B, C, and D? In B, we found this. C prime parentheses 1 is negative 0.91. So remember from the picture at the start of the video, this number that's this value, this derivative, is the number that's the slope of a tangent line. The tangent line that's tangent at t equals 1. So we illustrate this result by drawing that tangent line and labeling it with its slope. And our result from C prime parentheses 4 is minus 0.2. That's the slope of the tangent line at t equals 4. Now what about our result from D? Question D, we found an average rate of change, and it was this quantity. That's the slope of a secant line, so we illustrate that by drawing the secant line and finding its slope. So there you see those three lines with their slopes. Notice that it makes sense that this slope is the most negative, this slope is not as negative, and this slope is not very negative at all, because those lines are less steep as you go across. All right, well, that's the end of this example, and that's the end of the video. Thank you.